Welcome to this explainer. Okay, today we're looking at something truly mind-bending. For literally all of human history, aging has just been this inescapable fact of life, right? A slow, inevitable decline. But what if we completely flip the script? What if, instead of looking at the human body as this fragile organism that's just destined to break down, we started treating it like a machine? Think of it like a highly advanced biological computer that can actually be maintained, debugged, and remarkably upgraded. The science we're unpacking today suggests that drastically extending human life is no longer just theoretical. It's actually about applying specific, measurable upgrades to our biological systems. So, can we reprogram the human body to live 120 healthy years? I know, it sounds like pure science fiction, but recent, absolutely stunning breakthroughs in cellular biology are turning this exact question into a highly active clinical pursuit. We aren't just talking about tacking on a few extra fragile years at the end of life. No, we're talking about fundamentally altering how our cells operate on a day-to-day basis. Okay, let's dive into this because understanding this distinction is pretty much everything. Notice that we aren't just saying lifespan. If we're extending life, literally nobody wants those extra decades to be spent in frailty or endlessly battling chronic disease. The true metric scientists are obsessively chasing right now is health span, meaning the period of life spent in vibrant, optimized health. The goal isn't merely surviving to 120, it's about upgrading the human machine for absolute peak performance right up until the very end. To run this system diagnostic, here's our checklist. First, upgrading the human machine. 2, recharging the power supply. 3, clearing corrupted cellular hardware. 4, rebooting the epigenetics software. 5, the leap to human trials. And finally, 6, the 120-year health span. All right, let's jump right in. Moving to step 1 of our diagnostic, recharging the power supply. Specifically, restoring cellular energy with NAD+. And this brilliantly illustrates the core issue. Just like a smartphone whose battery drains way faster the older it gets, our cells experience a severe energetic crisis as we age. On the one hand, you've got a youthful cell. It's glowing, highly energized, and running super efficiently. It boasts a massive ratio of a vital molecule called NAD+. You can think of NAD+ as the premium fuel for our mitochondria, which are the cell's power plants, and it's absolutely crucial for DNA repair. But contrast that with an aging cell. It is in a full-blown energetic crisis. As we get older, accumulated DNA damage hyperactivates repair enzymes called PARPs, while chronic inflammation triggers another enzyme called CD38. Basically, both of these act exactly like rogue background apps on your phone, just greedily draining your NAD+ battery reserves much faster than you can ever replenish them. So, the big question, how do we plug the human machine back in? Well, the science points to a few proven interventions to recharge our biological battery. First up, we can actually synthesize new NAD+ using vitamin B3 precursors, specifically molecules you might have heard of, like NR and NMN. Imagine these as premium fuel additives that completely bypass our aging broken down synthesis pathways. Second, lifestyle modulators. Things like caloric restriction and endurance exercise naturally stimulate the pathways that recycle NAD+. And finally, targeted inhibitors are currently being developed to block that CD38 enzyme, effectively force-quitting that rogue app that's draining the battery in the first place. And let me tell you, the results of these interventions are far from theoretical. Early human trials confirm that daily supplementation with these NAD+ precursors safely raises blood and tissue NAD+ levels by an incredible 50 to 100%. That is a massive margin, and it translates to measurable, real-world gains in muscle insulin sensitivity and aerobic capacity. We are quite literally restoring the cellular power supply. Which brings us to part 2, clearing corrupted cellular hardware, focusing on precision senolytics and so-called zombie cells. You see, over time, our bodies accumulate damaged cells that act a lot like corrupted hardware or bad sectors on a computer's hard drive. In biology, we call these senescent cells, or much more colorfully, zombie cells. These are cells that have suffered intense stress or DNA damage and have permanently stopped dividing. But here's the catch. They refuse to die. Instead, they just linger there, remaining metabolically active and secreting this incredibly toxic cocktail of inflammatory molecules known as SASP. They essentially drag down all the perfectly healthy tissue around them, acting as a massive driver for the chronic inflammation we always associate with aging. But here is a truly fascinating twist. We used to think we just needed to carpet bomb all these zombie cells out of existence. But recent science reveals they actually aren't all bad. In fact, some senescent cells are highly beneficial. They help with wound healing, they maintain tissue balance, and they even guide embryonic development. So the future of anti-aging medicine isn't about total eradication. It's about precision geroprotection. The trick is using targeted therapies to clear out only the corrupted zombie cells, the ones actively fueling tissue degeneration and metabolic disorders, while leaving the helpful ones completely intact to keep doing their jobs. Now, what's really interesting about this slide is that the real-world application of this concept is already here. This clinical trial abstract highlights the effects of a groundbreaking therapy class called senolytics. Specifically, researchers took a cancer drug called dasatinib and combined it with a natural plant compound called quercetin. And when they administered this to human volunteers, the specific combination successfully demonstrated an obvious senolytic effect. It selectively induced apoptosis, which is essentially programmed cell death in those harmful, corrupted cells. And that led to genuinely improved physical capacity in the patients. We are actively defragmenting the human hard drive, folks. All right, on to part 3. Rebooting the epigenetic software through the magic of cellular reprogramming. So, okay, we have power and we've cleaned up the hardware. But what if the core operating system itself is just full of bugs? That brings us to the ultimate biological fix. I want you to think of your DNA as the hard-coded hardware and your epigenome as the software that tells that hardware what to do. As we age, these chemical tags, specifically methyl groups, start accumulating on our DNA. These tags act like tiny switches, and over time, they wrongly turn off our youthful genes and turn on aging genes. It's a glitchy OS. To fix this, scientists are utilizing a modified version of the CRISPR gene editing tool. But here's the genius part. Rather than physically cutting the DNA strand, which carries a lot of risk, this new epigenetic editing simply removes or adds those methyl tags. It essentially brushes the biological cobwebs off the genes, switching the youthful code back on without ever altering the underlying hardware. The absolute most profound application of this is known as cellular reprogramming. Back in 2006, a scientist named Shinya Yamanaka discovered 4 specific proteins, now famous as the Yamanaka factors, that can actually reprogram an adult cell all the way back to an embryonic stem cell. But for anti-aging, we definitely don't want a total factory reset. An eye cell still needs to remember it's an eye cell. So scientists use partial reprogramming. Step 1, you apply the Yamanaka factors. Step 2, you let them rewind the epigenetic clock, gently scrubbing away those age-related chemical tags. And step 3, and this is absolutely vital, you stop the process just before the cell forgets its specialized identity. What you're left with is a cell that knows exactly what its job is, but acts like a brand new, young version of itself. And the wildest part is, we can actually measure this software reboot in real time. This massive review by researchers Adiv Johnson and David Sinclair took a hard look at next-generation epigenetic aging clocks. These are highly accurate, predictive models that measure those specific DNA methylation tags to determine someone's true biological age. And their review proves beyond a doubt that this is a rapidly advancing field, tracking real, measurable biological age reversal. Whether through targeted therapeutics, lifestyle interventions, or eventually this kind of cellular reprogramming, we aren't just slowing the aging clock down anymore, we are measurably rewinding it. Let's move to section 4, the leap to human trials, taking this from the lab bench to clinical reality. Let's move to and see how this builds into something that actually impacts you, because the trajectory here is just astonishing. In 2006, Shinya Yamanaka first demonstrates this OSKM reprogramming in a petri dish. Just 6 years later, in 2012, he wins the Nobel Prize in medicine for it. And now, slated for 2026, a company called Life Biosciences has initiated FDA-cleared in-human trials using this exact technology. I mean, in the grand scheme of medical history, moving from a fundamental, groundbreaking biological discovery to actual human trials in just 20 years, that is absolutely blistering speed. And here is what they are actively doing with it right now. Life Biosciences is testing their therapy, called ER100, in human patients. They are specifically targeting age-related vision loss, things like glaucoma and optic neuropathy. By essentially injecting this epigenetic software upgrade directly into the eye, they're attempting to reverse aging in the retinal neurons that connect the eye to the brain. The goal is restoring youthful function and potentially even restoring lost sight. Make no mistake, they are actively testing an operating system upgrade in humans today. Which brings us to our final section, the 120-year health span and reaching what's known as longevity escape velocity. As we start synthesizing how the power supply, the hardware clearance, and the software reboot all seamlessly come together, I want you to really absorb this quote from Dr. George Church. He's a pioneering geneticist over at Harvard. He says, "We cannot rule out the possibility that humans have already reached longevity escape velocity, where we add a year to lifespan each passing year." Now, longevity escape velocity is this profoundly wild mathematical threshold. It essentially means that science is advancing so rapidly that for every single year you stay alive, medical technology extends your remaining lifespan by more than a year. And according to Dr. Church, because we're increasingly using AI to design way more efficient delivery techniques and cut down on drug toxicity, FDA approvals are speeding up so dramatically that we might actually be crossing this threshold right now. So, the crucial point is this. Aging is not one single point of failure. It is entirely multifactorial. The ultimate biological upgrade requires us to target all these interconnected pathways simultaneously. We absolutely must recharge the system by boosting NAD+ to restore cellular energy. We have to defragment the body by using senolytics to clear out those corrupted, inflammatory zombie cells. And we must reboot the system using epigenetic reprogramming to reset our DNA software. By applying this kind of comprehensive, full-body maintenance schedule to the human machine, achieving a disease-free, high-functioning 120-year health span is no longer just a pipe dream. It is the literal stated goal of modern geroscience. Which leaves us with a deeply provocative question to ponder as we wrap up. We've spent our time today looking at the biology, the mechanisms, and the clinical trials. But if science successfully executes this upgrade, if we truly master our cellular hardware, our software, and our power supply, what happens next? What does our society, our economy, and honestly, our entire human experience look like when living to 120 becomes the new 80? It's a breathtaking future to imagine, and as we've seen today, it might be arriving much, much sooner than we think. Thank you so much for joining me for this explainer, and keep your eyes on the science. It is moving incredibly fast.